David Schaefer. This is my dissertation defense. It's titled Pressurized Testing of Tubular Solid Oxide Fuel Cells Using Ammonia and Jet Fuel for Development of a Hybrid Gas Turbine Propulsion System Model. So a little bit of sort of motivation. This work is a part of what's called the NASA CLEAN project, where CLEAN sort of loosely stands for CarbonLess Electric Aviation. And the goal of this project, what NASA was looking for, is the next generation of propulsion for the most common sort of aircraft in the US, which is like a single aisle passenger aircraft like the Boeing 737. So for this first part of this project, trying to come up with a new propulsion system, maybe we're using future fuels, more efficient, that sort of thing, but we're trying to retrofit onto a Boeing 737, hopefully allowing the technology to get to market faster. So the CLEAN project, which in the bottom right, whole group of people, lots of different universities and companies, the solution we came up with is an SOFC gas turbine or a solid oxide fuel cell gas turbine hybrid system. In particular, it's a turbofan, which you can see sort of a mock-up on the right. Now, the initial goal of this project was to be carbonless or carbon-free. So originally, we were going to use ammonia as a fuel because that's just NH3, so you don't have any carbon in there. And so we didn't want to have any carbon emissions, so we were looking at ammonia. As the project progressed, though, we really saw how advantageous it was that the SOFC and the gas turbine can both be fuel flexible. So we sort of morphed the project into looking more at multiple fuels. So, a really far future fuel like hydrogen, maybe a less as far away future fuel of ammonia, and then current day fuel of jet fuel. And if we can get that jet fuel working, that makes this technology very versatile because it could be used today with sort of no change in infrastructure, or at least less change in infrastructure. So what I'm going to talk about today, we're going to give a little background first, then I'm going to introduce the overarching clean steady state system model. So this is a thermodynamic model that models that entire SOFC gas turbine system. Then we're going to work on introducing an SOFC sizing model and an SOFC performance model, basically figuring out how we can implement the information on the solid oxide fuel cells into this hybrid system model. Now we'll do all that with what we already know on hydrogen, both in the work in this lab and just, hydrogen work on fuel cells is pretty extensive already in literature, but we don't know how they work on ammonia and jet fuel yet. So we'll have to go into actually testing these SOFCs on ammonia and jet fuel. We'll do a lot of tests. We'll talk about that. We'll see what we learn, and then we'll take what we learn and basically re-update those submodels for the SOFC submodels. And once we've updated those submodels for these new fuels, we'll rerun the full system model, so the whole SOFC gas turbine system model on these three different fuels of hydrogen, ammonia, and jet fuel. So that leads into what the research questions are. Basically, just trying to figure out how ammonia and jet fuel affect solid oxide fuel cells and SOFC gas turbine systems. So these first three sub-questions are all about the solid oxide fuel cell. Part A, plain and simple, how does pressurized operation of fuel cells change with these different fuels? Part B and C here, basically looking at how the fuel pre-processing and the different operating conditions affect the fuel pre-processing, and then how that fuel pre-processing affects the SOFC performance. Part D is basically how can we integrate the SOFC characteristics into the system model with our sizing and our performance model. And then part E, how do those models change between these different fuels? And then how does the full system change between these different fuels? So now I'll just jump straight into some background. First off, probably most important, what is a fuel cell? So a fuel cell is an electrochemical device that produces electricity and steam from hydrogen and oxygen. Typically that oxygen comes from air. You can think of it similar to a battery. Your reactants instead, though, are continuously flowing rather than all being constrained within like a battery. A solid oxide fuel cell is a particular variant of fuel cell known for operating at high temperatures around 600 to 1,000 degrees Celsius. And to do this, they're typically made of ceramic material. Now, these fuel cells can come in a few different shapes and sizes. The most common one is called planar. And so that's pretty similar to a sheet of paper. One side is an anode, one side is a cathode. Maybe the second most common is tubular. And that's what we have up here, and that's what we'll work with today. Basically, it's you take that sheet of paper and roll it into a cylinder. Another one of note is what's called button cells. These are basically planar cells that are really small, like the size of a shirt button. And those are often used for rapid testing and rapid development. A couple key parameters to note with fuel cells. Active area is a parameter I'll talk a lot about today. And so active area is basically the surface area that the reaction is actually happening. This will be given in centimeters squared, and it's basically the size of the fuel cell. Another important one is power density. So this is taking the power that the fuel cell is producing and dividing by that active area, sort of normalizing it by its size. And this will be done in watts per centimeter squared. So now for a hybrid system of SOFC gas turbine, why are we interested in that? Why do we want to use that? Well, its efficiencies can get upwards of 70%, which is higher than both the gas turbine and the SOFC individually. So that's pretty good. Want to go into those fuel savings. And the reason we're able to get that high efficiency with this sort of hybridization is that the solid oxide fuel cells and the gas turbines kind of complement each other. So SOFCs operate at those high temperatures, and then the turbine and the gas turbine benefits from high temperature flow to provide shaft power. Additionally, you have compressed flow within the gas turbine. You have a compressor compressing air, and SOFCs are known to have higher peak power with increased operating pressure. So kind of two things there of temperature and pressure that can benefit the SOFC system. There are many different versions that have been proposed, a lot of different models, a lot of different variations. They can go anywhere from an SOFC and a gas turbine connected by a heat exchanger, or to fully integrated, kind of like what's shown here in the top right, where the SOFC is sort of integrated into the combustion portion of the gas turbine. And that's more so what we'll have here, but I'll talk about that in a second. So I said we were interested in three fuels: hydrogen, ammonia, and jet fuel. So a lot is known about hydrogen already, but you may not know why we're interested in ammonia. So ammonia is what's known as a hydrogen carrier. We're basically using it to get the hydrogen out of it. So it's NH3. You can break it down to get N2 and H3 or H2. But the reason we're using it is it has better volumetric energy densities. So it's a little easier to store, especially when you're constrained volumetrically, like when we're retrofitting to a Boeing 737, where we're trying not to change the plane size. Additionally, ammonia has a lot more infrastructure already than hydrogen does. So it's heavily used in agriculture, heavily used in shipping, especially in Asia, and even in HVAC. Now, to get it to break down into that hydrogen that we're going to use in the fuel cell, there's a couple ways to do it, or a few ways to do it. The most common or simplest is to just get it hot. So you can thermally crack it or thermally decompose the ammonia. And this is usually done around 700 to 900 degrees Celsius. But if you add a catalyst, you can lower that temperature required to do that. Now, jet fuel, I kind of explained, we're very interested in that because it'll make this technology pretty versatile, even in today's world. But to use jet fuel and heavy hydrocarbons in SOFCs, you have to do a few things first. So the end goal is to get the hydrogen out of it, just like with ammonia. But to do that, we have to actually add either water or steam to do steam reformation, or we have to add oxygen, through air to do partial oxidation. Now, steam reformation is endothermic, and partial oxidation is exothermic. So sometimes you want to balance both of those to sort of balance out the temperature of your catalyst, because that's also important. Some of those reactions are shown on the right, but in reality, there's a whole ton of reactions because you're trying to break down a long hydrocarbon chain. Usually jet fuel is considered around, C10H22 or something like that. So we have a couple major concerns to watch out for when using heavy hydrocarbons like jet fuel in SOFCs. The first one is carbon formation. So when you're breaking down that hydrocarbon, you can get solid carbon in the form of soot. And that's bad because that can block active sites on the catalyst as well as in the fuel cell itself. So basically reducing your performance of decomposing the jet fuel and then reducing your performance of your fuel cell. Luckily though, in literature, we found sort of a map or a guideline on how to watch out for that. And that's shown here in the right. Basically, it's a factor or function of our oxygen to carbon ratio. So the amount of air we're flowing compared to the amount of carbon in the jet fuel we're flowing. And then our steam to carbon ratio, same thing, but with steam. And you can see we have a bunch of different temperature lines, and we want to be in this region up here called the carbon-free region. So if we're operating at a condition in this carbon-free region, in theory, we are not building solid carbon. And if we're operating below these lines, then we might be building, or probably will be building, solid carbon. Another important thing to note is desulfurization. So jet fuel actually has sulfur in it, but sulfur is a known poison to SOFCs and to some catalysts. So we're going to work with desulfurized, pre-desulfurized jet fuel in this work, but it's still important to note. So I'm going to go into a lot about SOFC testing. So I wanted to just provide a little bit of basic background on how we're doing that testing. So sort of the go-to testing method for fuel cells is what's called VI curves, or sometimes IV curves or polarization curves. Basically, we're looking at the voltage and the current, and we're going to vary one of them and see the response of the other. In the case of this work, we're going to vary current, so we're going to load the cell more and more and more, and we're going to see and watch the voltage drop with each increase in load. And so you'll end up with a curve, something like this blue line here in the top right. And what this allows us to do is allows us to characterize the total loss of the cell, but it also allows us to find something called peak power, basically the max amount of power that this cell can make. And we'll actually use peak power density, like I was mentioning earlier. Another important thing to note with these VI curves is that we can run at a constant fuel flow or a constant fuel utilization. So fuel utilization is this equation down here. Basically, it's how much fuel you're using in the fuel cell and how much is actually exiting the fuel cell. So a constant fuel flow VI curve will run the same amount of fuel no matter the load. So it's constant. Constant fuel utilization VI curve, you'll keep that fuel utilization the same through. So in the case of most of this testing, we use 50% fuel utilization. And what that means is half the fuel is being used by the fuel cell and the other half is exiting at the exit of the anode. And in the case of our testing, it's actually combusting. So as you increase the loading or increase the current here, you need to up your amount of fuel flow to be able to keep that same fuel utilization. So one of these, you have constant fuel flow, and the other, you're stepping up your fuel flow with your current. All right, so that was a little background, a little rapid fire, kind of all over the place, but hopefully prepares you well for the next few slides. We're going to jump into what this full system model looks like, the full SOFC gas turbine model, and then we're going to start getting into implementing the SOFC submodels into this model. So this is the full system model. Like I said, it's an SOFC gas turbine, in particular a turbofan. So we can see the turbofan aspects here, where we have a fan connected to a compressor, connected to a turbine via the shaft. You can see the bypass duct down here, which is what makes it a turbofan. And you can see the exhaust of the bypass duct and the turbine meet back together through a single nozzle. So that's pretty standard for a turbofan. The big difference here is in the combustion region. So to sort of figure out how that works, we're going to follow our fuel flow, starting at the fuel tank, go through a couple of heat exchangers, because most of these fuels we either need to get up to the SOFC operating temperature or we need to get hot so we can decompose them. So if we keep going, you see there's a split point here where we can modulate how much flow goes to the anode here, the fuel cell, or goes to this mixing chamber. And this mixing chamber goes to what's called the post-combustor. And you can think of this kind of as a traditional combustor in a gas turbine setup. And basically modulating the fuel flow at this sort of intersection here lets us decide how much power we're getting out of the turbine by flowing more fuel to the turbine, or how much power we're getting out of the fuel cell by flowing more there. Which leads to a key parameter for this sort of testing, or this setup, sorry, and that's called power split. So power split is the amount of power being produced by solid oxide fuel cells compared to the total power. So if I say we're running a 15% power split, that means 15% of the power from the fuel cells and the other 85% from the turbine. So the fuel that goes through the fuel cell goes through the anode. A lot of that will be used, but typically you don't run 100% fuel utilization. So we'll still have excess fuel exiting the anode. That'll meet up with the compressed air from the compressor exit, and that'll go into what's called our pre-combustor. This is basically a very air-rich combustion, just trying to warm up that air a little bit before we get to the cathode side, where we need that air to be at SOFC operating temperature. Now for our electrical paths, the fuel cell produces DC power, gets sorted out through some power electronics, and hopefully get AC power going to the motor, which allows the fuel cell to provide power input to the shaft balance. So as I mentioned, there's quite a few people working on this project. So there's a lot of different teams, and that's because there's so much that has to go into this. So there's a lot of different models that go into this overarching system model here, which is shown here. You know, we have a structural system model, and we have an aerodynamic system model, we have tank sizing. Today, I'm just going to focus on the solid oxide fuel cell portions, so the SOFC sizing and the SOFC performance model. So we're going to primarily focus on that, and then we're going to look into, you know, how that affects the full system model and how that affects the full system model performance. All right. So with the full system model sort of explained, I'll go into the SOFC sizing model. So we want to size the entire engine to figure out its mass or its weight and the diameter of the engine. So to do this, we had to get some CAD, some sort of basic design of the fuel cells, and that's shown here in the top right. And this is kind of a unique design because we have the SOFCs stored in the nacelle of the engine. And you can see the SOFCs here with these green tubes. They're basically stored in rows and columns. Those rows and columns are stored in these boxes, and then these boxes are stored in what's called box rows, and then those box rows go around the annulus there around in the nacelle. And then if you have a really high SOFC power system, then you'll have multiple layers of these box rows. So to figure out the size of this engine, I had to create a sizing model, or you can think of it as a physics and geometry model. So it takes into account the geometry of these boxes, the rows and columns, figures out, what's the spacing of all of it, how much does it weigh, but it also does some physics. So this annulus has to be an annulus pressure vessel because we're going to operate at elevated pressures, and it also has to operate at high temperatures. So there's a thermal circuit in there involved. You have fuel cell temperature, insulation, and then your actual pressure vessel. And then, of course, we have to consider the pressure vessel's yield strength and factor of safety and things like that. So all of that is wrapped up into one model that gives us our mass of an engine and the outer diameter of the engine, which is good, but that's kind of hard to implement into the full system model. It's kind of computationally expensive, especially if you've ever played with ease. When you start adding a lot more variables, it gets a little pickier. So we want to try to simplify this down. Ideally, if we could get one equation that just gives us the mass of the engine and another equation that gives us the outer diameter of the engine, that would be great. But to do that, we need to figure out what those are primarily a function of, because we can't just take every input variable that we already have. Otherwise, we'd just be rebuilding this model again. So to figure out which ones were most important, did a sensitivity study of this geometry and physics model. Basically took a lot of these parameters that we thought were important over a range that we thought they might happen or occur at, and saw how they affected the mass and the diameter. And so that's what these two charts show. So you have sensitivity of mass here and sensitivity of outer diameter on the right. An important thing to note here is that SOFC active area I had to exclude from the sensitivity of mass because it was 560% of an effect on mass, and that kind of skewed everything else in the chart. As you can see, the second biggest one is only 65 or 67%. So using this, we can determine what the most important factors are to have as inputs for our surrogate equations that we're going to make. So clearly, SOFC active area is most important, so we need to have that. And that makes sense. That sizes the amount of SOFCs in this system, which is, primarily where most of your outer diameter and mass come from. You can see over here, though, nacelle length is also important. Fan diameter is important, which again makes sense because that fan diameter sets the inside diameter of our annulus. So that's really going to affect the diameter, the outside diameter. And then you see SOFC rows. So this one's kind of interesting because the thermal model doesn't really care about the rows and columns of the fuel cells. It doesn't really care how they're organized. So that's only internal to this geometry model. So we'll have to figure out a way to kind of take that into account because we can't have that as an input from the thermal model. So what I did was, EASE actually has a built-in genetic algorithm, and we took these four parameters shown here in the bottom right and basically ran the physics and geometry model over this whole working ranges, a mix of all points in this possible range, and then use that built-in genetic algorithm to optimize for the smallest mass times diameter by adjusting the rows and columns of the fuel cells in those boxes. So that's how we get an optimized design that takes into account the rows and columns of the fuel cells. So that leaves us with a large data set of these optimized engines. And then with that data set, we can easily just fit a regression to that or a surrogate model to that and get a couple equations. So these equations are quite large for mass and diameter, but you can at least see some of the equation statistics down here. R squared of 9.9 and 9.9 on both. And then there's our errors as well. So now we have the SOFC sizing implemented. Now we need to look at SOFC performance implementation. We're going to do this to start with on hydrogen, just because we already had the hydrogen data that we could work with. So we aggregated some of that hydrogen data, all of which was the same operating conditions, 750 degrees Celsius, 50% fuel utilization, and obviously hydrogen. And then the problem with that is sometimes these cells perform differently. We have better cells, we have worse cells. Sometimes these tests perform differently. The cell performs better in one than the other. So we need to normalize that. So we took all of these and basically normalized by the peak power at 1 bar. So that's this blue dot right here. And so that's why our current density at that point is now 1, and our power density at that point is also 1. And everything is made relative to that. So that's why 2, 3, and 4 bar here are all higher, because we perform better at higher pressures. So you're going to end up with a number greater than 1. This actually works out really well for us because as we work through this and implement this into the overall system model, it gives us a knob we can turn of basically how good the fuel cells are in the system model. So we can pretty much set the peak power density and then change that between scenarios we want to run. We could say present day scenario, about 0.5 watt per centimeter squared or something like that. Maybe 5 years from now, a full watt per centimeter squared, and then maybe 20 years from now, we got 2 watts per centimeter squared. So it lets us vary that in the system model, which is great. All right, now to fit an equation to that data, try to take a physics-inspired approach, trying to use some commonly used parameters that are in SOFC equations, but not making it too complicated. So this equation up here, you can see, is voltage over the voltage at peak power, not to be confused with peak voltage. It's actually the lowest voltage or near the lowest voltage. So this is the normalization that we were doing having an effect here. If you want to simplify it, you can kind of think of just these terms as voltage and just this term as current density here with J. It's just normalized. So we have this first part with a constant plus a constant times the natural log of pressure. This is kind of similar to what you might see in an Ernst overpotential. We have the second term where you have a constant, maybe a resistance times a current density. That's pretty similar to what you'd see in an ohmic loss. And then we have this last term here where it looks similar to something you might see with current limiting or limiting current equations, something like the Butler-Volmer or concentration loss. And then to get power density here, we just multiply that voltage equation by current density. And so you can see that down here, power density over that peak power density, again, just our normalization, equals that current density normalized times that voltage. And you can see some of our coefficients up here in the top right. So we took that fit and tried to look at how well it fit to the data we were fitting it to. You can see all the fit lines in one plot, kind of a mess right here. But a key part here is we actually had to extrapolate out to 11 bar. So we can only test to 4 bar, but our system model we already knew is going to go upwards of 11 bar. And we just wanted to make sure that this fit equation, didn't get erroneous or crazy when we went too far out of its region or out of its training set. You can see it split between the 4 different pressures here. Visually matches up pretty well, so that's good to see. Then we look at sort of the residuals here, the curve fit error, and most of our error is below 5%. So that's really good to see, especially considering how chaotic or crazy testing data can be sometimes. And then again, some of our fit equation statistics are there shown on the left. And you see 2 different ones for voltage and power, just because that equation, it's like one equation that's used in those 2 equations. All right, so now we've implemented SOFC sizing, we've implemented SOFC performance, but all of that's on hydrogen. That's all on stuff we already know. So we need to look into what happens when we go to ammonia, what happens when we go to jet fuel, what changes. But before we get into testing of the fuel cells for that, we of course want to see what other people have already done. So there has been some ammonia testing on SOFCs, a few that use tubular cells. Unfortunately, these are all at ambient pressure and we want to see pressurized data, but it's still important to look at. So they found that the ammonia performance was anywhere from 75 to 99% of the hydrogen performance. Basically, the peak power was that percentage lower. But these were pretty small cells. One didn't tell us, and the other was about 3¼ centimeters squared, which is a really small amount of active area. We were able to find some pressurized data performance, which is actually shown here in the bottom. But this is on a planar cell, still important to look at, see what they saw. So this work was done by Shai and Hung, and they tested simulated ammonia compared to pure ammonia. Simulated ammonia is nitrogen and hydrogen flown together at the same stoichiometric ratio as ammonia, but it's already separated out. They found that there is a power difference of about 2% between simulated ammonia and regular ammonia. And you can see that with these yellow lines on this chart. It's there, it's kind of hard to see, but looking at this red point here. And their cells were a little bigger, 25 centimeters squared, but again, kind of on the smaller side. Now for hydrocarbon testing, there's a lot of tests that's been done on methane, even in our own research group here. And that's just because methane has a lot of interest, especially in the US. But the problem with that is it doesn't really compare to the heavy hydrocarbons as well, because CH4 is easier to break down into hydrogen than, say, C11H22. So when we do start looking at heavier hydrocarbon testing, a lot of groups use what's called syngas, or synthetic gas. And so this is either like simulating what jet fuel is when it's already decomposed, like just flowing CO2, CO, H2, H2O, that sort of thing, or they're decomposing it prior and then like in a separate system and then sending it to the fuel cell. There were a couple of works that used heavy hydrocarbons and decomposed them in line with the fuel cell. So one work here used Pennsylvania crude oil and JP7 and JP8, and now those JPs are just a military jet fuel, so definitely of interest because we're trying to do jet fuel here. Their active area was tiny. It was about 0.2 centimeters squared, so definitely a button cell. Unfortunately, their work, is relevant, but doesn't really help us because they focused on the sulfur content and the sulfur poisoning, and that's not really what we want to focus on with this work just yet. Another group used dry gasified coal. They had a much bigger active area of 24 centimeters squared, and they were able to, produce power with it, but they didn't provide any comparison to hydrogen. So it was more of a, yes, we can do this, and not a, okay, how does it perform compared to hydrogen? They also suffered from some sulfur poisoning. There have been a few JP8 SOC systems, again, military jet fuel, that have been made, but they all operate at atmospheric conditions, and sometimes you get a little iffy on the public availability of that information just because they end up being a part of industry or a part of the military. So we found a few gaps to get what we want out of this testing. So we need to address these gaps in our testing. For ammonia, there's no pressurized tubular testing, so we need to do that. And they're also only using smaller size cells, less than 25 centimeters squared. So we want to try and push this to active areas that are larger, more like something that would be in a real system. Additionally, they don't really talk about if ammonia is decomposed or how it's decomposed. If they're using a catalyst, if they're not using a catalyst, and they don't talk about how that decomposition affects performance, which we'll see is kind of important. For jet fuel, the gap is kind of larger here. There's just no publicly available pressurized SOFC data using jet fuel, period. Like I mentioned, there's some syngas data, but not data where the jet fuel is decomposed in line. So we're going to try to address some of these gaps with the SOC testing in this work. So to do that, we obviously need the setup to test these SOCs. So we'll show that here. So this is Tennessee Tech's pressurized solid oxide fuel cell test stand. It's actually on the first floor of this building that we're in today, unless you're online. And you can see it here. And it's basically a giant pressure vessel, kind of looks like it's wrapped in aluminum foil here. And that pressure vessel has a cutaway right here. And you can see it's got a big, large heater, and then an inner vessel. And then this green tube is a mock-up for the fuel cell in the test setup. So the fuel flow comes up the middle, goes to this fuel cell, goes through this reformer or catalyst holder, and it can also be sampled off for a mass spec, but we'll talk about that later. The air comes up through this blue tube, goes through a heat exchanger here. Basically, our anode exhaust is combusting, so we're trying to take advantage of some of that heat just to help heat up our air to SOC operating temperature. And again, these are the tubular cells we're using. These cells are provided by a company called Special Power Sources, or SPS. They're 15 millimeters in diameter, and for the most part, the active area of the cells we're using is about 88 centimeters squared, but we do use a couple that are smaller, about 44 centimeters squared. We can operate this test stand up to 800 degrees Celsius for our fuel cell operating temperature. Of course, we can use multiple fuels. That's the whole point of this testing. And we can pressurize up to 4 bar using a pressure regulator in our exhaust. We typically, do VI curves. I kind of mentioned that earlier. And for most testing, we use constant fuel utilization, but for jet fuel, we'll actually use constant fuel flow. We'll talk about that in a second. So for ammonia testing, we basically just had to integrate an ammonia mass flow controller. This had to be a corrosion resistant mass flow controller because it's ammonia. And we actually ended up having to have a whole sort of board and system to implement that. So that's shown up here in the top right. I'll call this the ammonia board. And what it is it takes ammonia from the fuel tanks, has a mass flow controller, has a whole bunch of valves and solenoids, which allow us to integrate nitrogen. And we want to integrate nitrogen in case of emergency. We want to purge the ammonia out of there or dilute it. And then when we're done testing, so when we're done using ammonia, we want nitrogen to get all the ammonia out of there so that we're not, messing with ammonia if we're to say adjust things on this board. You can see a fuel cell actually implemented into the test stand down here on the right with its silver wires and its current and voltage taps. You can also see some of the thermocouples that are on the outside of the fuel cell, which let us set the operating temperature of the fuel cell. And you can see this catalyst holder or reformer in the case of jet fuel right here. So this catalyst holder is pretty much a stainless steel cylinder, has one inlet in the bottom for fuel flow, two outlets on top, one that goes to the anode of the fuel cell and the other that goes to the mass spectrometer. As you'll see in a few slides, we end up needing a catalyst for our ammonia testing. So we use nickel foam catalyst when we do. And you can see it's kind of spiralized here because we have a thermocouple that actually comes up through the center of that catalyst holder. And if we're doing a test where there wasn't a catalyst, we still had this catalyst holder, but it was empty, just trying to keep consistency. And, these fittings get interesting when you heat them up this hot. Now, I'd love to talk a lot about safety because there was a lot of work that went into this, like 3 to 6 months worth of work. But for the sake of time, I just want to say there was a lot considered with safety because I always get questions about it, and rightfully so. This is ammonia. But just want to say we did a lot. We can talk about it more. Please ask about it. For the jet fuel testing, the biggest difference here is we're now dealing with liquids. So we have to have liquid mass flow controllers, but we also have to have a vaporization system. And that's shown here in this PNID, but also here in this picture. And the way we do this is we have 2 cartridge heaters, one for jet fuel, one for water. Then we have a coil going around it where our flow is, and that's what vaporizes it. And then those vaporized flows meet together through a single tube, and then that tube has heat tape around the outside just to try to keep the temperature of the flow up, and then it meets up with the regular anode flow up into the fuel cell. For all of our jet fuel testing, we used a catalyst. It was this platinum rhodium catalyst on an alumina support. You can see the monolith here. And if you have a good eye and look closely, you can actually see the thermocouple poking through the center of that. But otherwise, very similar setup to our other testing. So we've talked about the physical testing setup. I just want to briefly touch on the procedural setup. Every one of these tests was kind of run the same start plan, and that started, of course, with warm up. So we had to get up to 750 degrees Celsius. This usually took us about an hour. And then once we got up to a temperature, we gave it another hour for the fuel cell to stabilize. So it was just sitting there at open circuit voltage, or OCV, unloaded. Once both of those hours were up, we then did a 30-minute constant load on the cell. So gave the cell usually around 5-10 amps, basically get the voltage down to 0.85 or 0.9 volts, sort of letting it warm up in a metaphorical sense rather than a literal sense here. Additionally, or once all that was completed, our test really began. And the first thing we did with the test was run what I'll call a baseline VI curve. So this is a VI curve that's run on hydrogen, around 50% fuel utilization, ambient pressure, 750 degrees Celsius, and is run right there at the beginning. And the reason we're doing this is everything else in the test can be referred to relative to that. So we'll normalize all the peak powers of the other VI curves to the peak power of this VI curve. And that's important because these cells, between different cells, we can get very different performance. And even between the same cell and different tests, we can get different performance. So this kind of helps mitigate the effects of that. Like I mentioned, fuel utilization 50%. For jet fuel, we had to use constant fuel flow because it's a liquid and there's a lot more energy density in the liquid form. So we're flowing so little that we're just not able to do constant fuel utilization. All right, so now let's get into some of the testing results. We'll start with ammonia. So the first 2 ammonia tests we ran didn't have a catalyst yet, so empty catalyst holder. We have test 96 here, where we varied pressure, 1 to 4 bar, and then we varied fuel choice, hydrogen, simulated ammonia, and pure ammonia. We have test 97 here, same fuel choices, but we did a temperature sweep. So you can see that normalized point I was talking about right here with this blue square. That's that 100% for the hydrogen peak power. And everything is relative to that. So this chart's interesting because you can see that simulated ammonia seems to match up with the hydrogen performance, but pure ammonia seems to be a little bit lower, even outside the uncertainty of our measurements. So that's kind of weird. We'd think simulated ammonia and ammonia would perform the same, right? They're just the same thing, but the only difference is we have to decompose that ammonia. So we saw a similar thing here with the temperature sweep, but we wanted to investigate that decomposition of ammonia. So after this temperature sweep, we did another temperature sweep in test 97, where we connected the mass spectrometer to that catalyst holder exit. Again, remember, no catalyst here. And we were able to read basically what the fuel cell was seeing in its anode. So we can see ammonia here is the yellow curve or yellow dots. And our normal operating temperature of the fuel cell was 750 degrees Celsius, and our catalyst holder temperature was a little lower than that. So it was about 725. We're about 10% ammonia, so decent decomposition. But as we lower the temperature, that decomposition clearly gets worse, all the way up to almost 50% ammonia still in there. So that leads us to think, maybe this decomposition of the ammonia is what's affecting or causing the power difference between ammonia and hydrogen. So to improve the decomposition, we introduced that nickel foam catalyst I mentioned and ran the same two tests, another pressure sweep and another temperature sweep. And you can see here on the pressure sweep with the dashed lines, this is where we had the catalyst. Ammonia is actually showing that it's better, but these are all within the uncertainty of these measurements. So in reality, they're probably performing the exact same. In a temperature sweep, see something similar, other than this really low temperature point, ammonia seems to match up. Okay, so it seems like we fixed it with the catalyst, but we need to confirm this with another temperature sweep and the mass spectrometer to make sure we actually affected the decomposition. And it's clear we did. So if you look at our yellow curve again, ammonia, we're like less than 2% at our normal operating temperatures. And we don't even get above 10% until we're really far down in our temperature sweep. And these squares are just another test of the same thing that we ran later, sort of as a validation. So that shows us that adding the catalyst did what we thought it would do. It increased the decomposition of ammonia. And we're kind of hinting at the fact that when it's fully decomposed, ammonia performance can match that of hydrogen. But because a lot of these values are so close to each other, and we're at the point where we're having to worry about the uncertainty of our measurements, I employed the use of a statistical analysis, in this case a two-way ANOVA table or analysis of variance, to see if it could provide insight on this performance difference. So a very basic overview of this, picked an alpha value of 0.1. If our p-value is less than that alpha value, then that means that factor is statistically significant. So we'll just walk through here. Test 97, we have temperature, and so our p-value for temperature is 0. So that's way less than our 0.1. So what that means is that temperature is statistically significant to the peak power density of the cell, which makes sense. We saw that in the last charts. We already know that, of course, a high temperature fuel cell is going to be affected by its temperature. If we jump down to test 96, you can see pressure has the same p-value of pretty much 0. Again, already known, well written about, that pressure affects these fuel cells. But if you look at fuel choice in these two tests, we have p-values of 0.08 and pretty much 0. So what that's showing us is that the fuel choice between ammonia and hydrogen is statistically significant to the peak power density in these two tests at least. Now when we go to our catalyst test, test 98 and test 99 here, again, pressure and temperature, 0 for p-value. They're still going to have an effect. But our p-value for fuel choice is now 0.33, which means it's not statistically significant, or at least we cannot confirm that it's statistically significant. In test 99, our p-value was 0.14, and so that's maybe a little more borderline, but still on the side that's telling us fuel choice is no longer statistically significant. So again, showing us that when we have a catalyst, when we're addressing that decomposition of ammonia, there's no performance difference. So that was only the first 4 tests I ran on ammonia. There were quite a few more tests that I ran, and these charts kind of summarize all of them. So what this chart on the left here is showing, is the percent difference in an ammonia VI curve and a hydrogen VI curve at a comparable state. So we're no longer normalizing off of that baseline. We're comparing 2 identical operating points. So say 3 bar at 700 degrees Celsius on ammonia and 3 bar 700 degrees Celsius on hydrogen. And usually these 2 curves will run within 30 minutes of each other for comparison. So in this first column, we have catalyst. A little bit of a wider spread here, but it looks like the average is around 0% difference between ammonia and hydrogen. Matches up with what we're seeing, both in the statistics and just in the performance data. When we go to no catalyst, the range is a little wider and clearly is below 0. And that means that ammonia is performing worse than hydrogen. And our average, or median in this case, is at exactly -5%. Simulated ammonia lines up right at 0, which is what we saw. The simulated ammonia is performing the exact same as hydrogen. Now I had to separate out test 103 and test 104 here because we actually used a smaller fuel cell. So this fuel cell was only 44 centimeters squared of active area rather than the 88. And when I did the statistical analysis on these two tests, there was no significance in fuel choice, whether there was a catalyst or not, which didn't really line up with what we were seeing in the previous results. You can see here, test 103 with the catalyst does line up. It's 0% different on average, which is exactly what we'd expect. We can see a little more here in this chart than what the statistical analysis gave us for this test. It looks like when there's no catalyst in test 104 here, that there's a bit of a performance difference, but definitely not as big of a difference as the previous no catalyst. So that's interesting. Nothing really changed in the setup other than the fact that it was a smaller fuel cell. But if you'll remember, we're running a constant fuel utilization. So with a smaller cell, we're going to load that cell less because it's going to produce less power, which means we're going to flow less fuel. So we think that's where the difference came from. So that's where these two charts on the right come into play. And again, we have our percent difference to a comparative hydrogen state. And then the x-axis here is the flow rate of ammonia at that peak power condition, basically the max flow rate of ammonia. So this first chart with no catalyst, you can see these orange squares here are the small cell testing, a lot less flow. And you can see the percent difference is around 0, maybe a little less. But when we start to go into the larger cell testing, you can see that there is a drop-off related to that peak ammonia flow rate. If we look at the one with the catalyst, though, again, the orange squares are the small cell. These look right at 0. And as we increase the flow and go to the larger cell tests, they seem to stay around 0. So that clearly tells us that flow rate matters in the tests where there's no catalyst. And that further just develops the idea that this is all related to the decomposition of ammonia. So if you're not fully decomposing it, you're going to have a power difference. If you are fully decompose it, say you have a catalyst, or you're flowing a lot less ammonia, where it doesn't need as much energy to decompose it, you won't see that performance difference. Now we'll get into our jet fuel testing. So jet fuel testing was a lot more interesting to work with. Just having these liquids to deal with, having to vaporize them, having to deal with two-phase flow proved quite challenging. So the first few tests, we were actually having oscillations in our mass flow controllers, and that was purely due to orientation of everything. And I think we were having backflow of bubbles to our mass flow controllers, and they weren't able to deal with that two-phase flow. We were able to fix that pretty quickly, but oscillations continued in the voltage throughout all of our tests. So you can kind of see an example of that with this chart in the top right. So we have hydrogen open circuit voltage, again, no loading. It's pretty flat. We transition to jet fuel, gets a little crazy. Makes sense. We're transitioning to a two-phase flow, a different fuel. It settles a little bit, but there's still some oscillations. And here you can see the voltage is supposed to be going down in steps as we increase the current in steps, but the oscillations kind of blur it all into one line. For reference, here's a hydrogen VI curve where the steps are much straighter, much flatter, and we're actually able to run it a lot faster. That's why it's condensed. Interestingly, we noticed that when we increase pressure, this oscillation in voltage seemed to decrease. So this is a 1-bar VI curve again. You can't really see the steps there, but it's there somewhere. We went up to 2-bar in this blue section. Oscillations seem to be a little smaller. Going to 3-bar, they really seem smaller. And in 4-bar, you can actually kind of start to see the steps of the VI curve here. So we suspect that this issue is due to fuel flow rate. So the reason we say that is because the anode exit temperature where we're having combustion would also oscillate with this voltage. And so both of those are correlated to the fuel flow rate. And think this could be, or is most likely due to the two-phase flow. So, maybe we're having some sort of vapor lock issue. Maybe we have a cold spot in our fuel line where the fuel is recondensing for a second and causing these oscillations. We were still able to look at carbon formation. And we very quickly learned how to make carbon. It was quite fun. The first few tests, we only used steam. We didn't use air, and learned very quickly that we, in fact, need air based on this map here. And you can see those tests here. We produced a lot of carbon. You can see an example of the first test. Picture A is the catalyst before it's being used. So it's got kind of a gray, light gray color. And picture B, you can see the catalyst after the test where we've got this large ring of carbon. And actually below that, there's a kind of a pileup of solid carbon. You can also see it inside the anode of the fuel cell. We're able to swab off carbon. after the test. See that in picture C and D. And then in picture E here, we actually had carbon sort of splatter painted all over the cathode heat exchanger because the exit of the fuel cell is right here, and apparently we were sending a lot of carbon very fast out of that. Now we were able to get some tests where we didn't form much carbon, and even one test where we formed no visible carbon at all. So that was good to see. And those were these tests where we started, operating in the carbon-free region. Unfortunately, we were unable to do this at pressure. We tried, and we got a couple tests where there wasn't much carbon, but I think just with the instability in our flow and the dynamics of pressurization didn't quite play well with the carbon formation. For SOFC performance, this was very hard to characterize. So with that voltage oscillating so much, it makes it quite difficult to run these VI curves. We don't want to keep the cell at a voltage of like 0.3 volts because then we might be permanently damaging it and then ruining the results of the rest of the test. So these VI curves have an automatic, stop loading whenever the voltage is below half a volt. And so with those oscillations, a lot of times we'd oscillate to below that point, it would end the VI curve and we wouldn't get the full performance. One of our best ones though was our first test here, where you can see the jet fuel peak power increased with each pressure, which makes sense. That's cool to see. But you can see it doesn't really match up with the hydrogen performance. So, maybe we're learning something here, but we weren't able to validate that with any of the other tests just because the oscillations kept getting so bad. You can see another attempt to do that in test 93 down here, but our jet fuel performance at 3 bar is worse than our jet fuel performance at 2 bar, which it should not be. It should be better with each pressure. So basically this first bullet point here, it was sporadic, inconsistent, and indeterminate in how to figure out how it compared to hydrogen. All right, so for this next step, we'll sort of leave jet fuel behind, unfortunately, but we'll take ammonia and compare it to hydrogen, but we'll implement ammonia into the SOFC sizing, SOFC performance, and compare the system on hydrogen and ammonia. So to implement ammonia, we need to adjust these submodels. So the performance model was easy to adjust. We did nothing because the performance matched the hydrogen performance. However, to do that matching, we have to introduce a catalyst sizing to get that nickel foam catalyst so that we can minimize that performance difference. So this is just a simple equation based on gas hourly space velocity, used a value from literature just because our mass flow controller couldn't flow enough to actually test this value. Again, we're leaving jet fuel behind because we can't compare it to hydrogen at the moment, but we suspect it would be very similar. We'd have to have some sort of catalyst sizing. Having the fuel flow or the flows of water and air would be a little different, but a lot more work to be done there. All right, so now let's look at the system. Again, comparing ammonia and hydrogen. Ammonia is on the left here, hydrogen's on the right. This is our full system performance. Wish we had jet fuel here, but we'll see what ammonia does. So these top charts are plant efficiency, so total system efficiency, and you can see that ammonia has higher efficiency than hydrogen. So that's interesting to see. These bottom charts are range based on number of engines per wing. So traditionally you have 1 engine per wing, but because of the fuel cell system, a lot of times we end up at 2 engines per wing. And then the y-axis here is power split. Again, that's kind of the fuel cell sizing for the system. And we can see here that ammonia actually has a farther range than hydrogen, which is not what we expected. The hydrogen system actually has less mass because it doesn't have to deal with that catalyst mass. But hydrogen fuel tank storage and fuel storage in general is a lot heavier and a lot harder to do. You can see that in this next chart here. Again, ammonia on the left, hydrogen on the right, where you see the composition of our mass budget. Basically, our engine, our fuel tank, all on this one budget. And again, we're changing with power split, basically more fuel cells. So you can see, gas turbine's the same. You can see the catalyst implemented in the ammonia here. It's there, it's small, but it's not nothing. The fuel cell sizing between these two is roughly the same because again, they perform the same. But the biggest difference is this sort of teal color where the fuel tank takes up a whole lot more space. So the fuel tank assumption we're running with in this model is that of the fuel plus tank weight, 90% of that is actually tank weight. And that's actually kind of generous depending on who you ask, because current day tanks are around 95, maybe 97. Though there is a lot of work to get that number down to 85 and 80. Comparatively, ammonia is only 20% tank mass out of that tank plus fuel weight. so a lot less. So even though hydrogen has better gravimetric energy density or mass-based energy density, ammonia is able to store a lot more in this constrained volume of the Boeing 737 retrofit. All right, that leads into our conclusions here. So first off, just want to answer the research questions we set out to answer. So this first one, how did performance on these different fuels affect, or how did the SOFC performance on these different fuels change at pressure? We got ammonia to match up to hydrogen, and we saw that jet fuel is probably a little worse than hydrogen, but still working to 100% lay that out. Part B and C here, how did the fuel preprocessing affect SOFC performance? And how did different operating conditions affect this fuel preprocessing? Basically, we need to fully decompose ammonia in order to get it to match the hydrogen performance. And we can do that by either adding a catalyst or minimizing the flow if we don't have a catalyst. For jet fuel, we learned how to make carbon and how to not make carbon. We have to basically balance our oxygen to carbon ratio, our steam to carbon ratio, and that catalyst temperature. So a lot more intricate in setting up the jet fuel testing. Part D here, we showed how to integrate SOFC sizing and SOFC performance into this full system model. And then part E, we saw that the full system model seemed to perform better on ammonia than hydrogen. We sort of laid the foundation and the groundwork of how to implement jet fuel into this full system model. So that leads to contributions and implications. So the major contributions, this is the first pressurized testing of tubular SOFCs on ammonia. So that's pretty good to see. But really what's important is this is the first comparison between ammonia and hydrogen that actually talks about the decomposition of that ammonia. It's sort of looks at how that affects the performance. We do that with and without a catalyst, and then also we talked about flow rate. And though I've been maybe a little doom and gloom about jet fuel here at the end, what we did do is quite monumental, actually being the first group to do pressurized testing on jet fuel, where the Jet A is decomposed in line, and Jet A is just a type of jet fuel. Additionally, implemented SOFC testing performance and the multiple fuels on the multiple fuels into the full system model. So what does this mean? What is this? What are our implications? For ammonia, it shows that this could be a very practical aviation fuel. You know, it has a lot more infrastructure already set up. It seems like we can match the performance of hydrogen on fuel cells, and it seems like the full system may actually work better on ammonia than on hydrogen. We showed SOFC operation on jet fuel is definitely possible. We can get it in a state where we're not forming carbon. Still a little work to do that at pressure, but we think that's possible, and we know if we fix some of our two-phase flow issues, we can get there. And again, laying the foundation to be able to add in additional fuels to this full system model, like jet fuel, propane, or methane. So I want to thank the CLEAN project for funding a lot of this ammonia work. I want to thank Northrop Grumman for funding the jet fuel testing setup. And I want to thank Special Power Sources for providing the fuel cells. I couldn't have a dissertation here if I didn't have fuel cells to test. And then I want to thank the Putnam County Fire Department, Putnam County Emergency Management, Tennessee Tech's University PD, and their environmental health and safety team. You know, I said safety was kind of a big deal. There was a lot of meetings with these different groups trying to figure out we did this the best way possible. And of course, I want to thank the department and the PPATS lab here at Tennessee Tech. I kept saying we because there was multiple hands on all of this, partially because of the safety reason there had to be 2 people when we tested ammonia, but just in general, a huge thanks to them because they all helped out in making this work possible. Thank you guys for listening to my defense. If you want to fill out this defense presentation survey form, that really helps the department.